Hi students, now we are going to discuss about stability of different carbocations that are influenced by electron releasing group, electron withdrawing group, presence of alpha atom with respect to carbocation and presence of percentage of s orbital character with respect to carbocation, then number of groups and then power of the groups and distance of the groups from the carbocation. Right. About all these concepts, I am going to explain a clear crystal explanation, very easy to understand and retain the concept in our mind and easy to choose the correct answer without confusion in the examination. Okay, yeah, let's start now. Yeah. Take here a carbocation, carbon carrying positive charge. So 3 covalent bonds, 6 electrons, and here some Z atom is there, some Z. What is that Z? It is a electron releasing group or electron donating group. Okay, that means it releases electrons to the carbocation, releases electrons to the carbocation, right? So that electrons are negative charge, that negatively charged electrons neutralize or nullify the positive charge accumulate over the carbocation, then that stabilizes the carbocation, that increases stability of carbocation, right? Okay, so that if it releases electrons, the negative charge is dispersed over the positive charge on the carbocation, right? There is dispersal of the negative charge, dispersal of the charge on the carbocation, so that stabilizes the carbocation, that stabilizes carbocation, so that now the carbocation stability increases, that increases stability of carbocation, right? Yeah. Next one. If the another case, a carbon carrying positive charge, a 3 covalent 6 electrons, and it needs 2 electrons to get stability. Then to the carbocation, an atom X is bonded. It is a electron withdrawing group which withdraw electrons from the carbocation, right? So already the carbocation is unstable. It needs electrons. Again, electron withdrawing group is a bad friend. It is withdrawing electrons from the carbocation, like withdrawing money from the bank or from ATM. So already it is unstable. Again, it is taking electrons from the carbocation. It is going to more unstable. It destabilizes the carbocation, right? But here, a releasing group, it releases electrons so that it stabilizes. It is like a good friend. Electron releasing group is a good friend. So you want money, okay, to buy something, and to if you buy it and you eat it, you feel happy, you are stabilized. But you don't have that much of money. Then you have good friends are there. They give money, then you can go and buy the thing and you can eat it or consume it. Then you feel happy, you are stabilized, right? So good friends are there. They release this electron that easily stabilizes. But there is electron releasing group, but here is electron withdrawing group. It is withdrawing electrons. So that means you want to donate some money from to others, but you don't have that much of money. But again, you are made a friendship with bad friends. So what are the money you have? That money they are taking now. So that's why you are less amount now. You are going to more destabilize. Got my point, my dear students? Yeah. So that is the thing that is happening here. This electron withdrawing group withdraws electrons. Okay. So withdraw electrons from carbocation so that the charge, positive charge, okay, is intensifies. Positive charge intensifies means increase the positive charge. More positive charge means going to more unstable, right? That intensifies positive charge, intensifies positive charge on carbocation. So because of that, that destabilizes the carbocation. Destabilize carbocation. The carbocation is destabilized, then it is going to be unstable, more and more unstable, right? Okay, then decreases the stability of carbocation. We can say that decreases the stability of carbocation. Okay, my dear student, got it? Electron releasing group increases stability by releasing electron to the carbocation. Electron withdrawing group decreases stability by withdrawing electrons from the carbocation. Yeah, is it clear? Now we'll do some examples. We'll get the concept. We'll get clarity here with examples. So, for example, if a compound that is CH2, then here CH3 is there. This is carrying positive charge, and here CH2. And here CH2, and here NO2 group is there, it is carrying positive charge, and here CH2, right? Yeah. Now, this carbon carrying positive charge, right? Okay. Then this group to this carbocation who is bonded CH3, CH2, there is CH5 group is bonded. Now, this is a electron releasing group. It is a electron releasing group. There is a positive inductive affinity group, plus side group, positive inductive affinity group, and this is a alpha carbon adjacent to carbocation. Carbon is alpha carbon. Here two alpha hydrogens are present. So according to, if you apply hyperconjugation effect, so two alpha hydrogens are there. These alpha hydrogens are stabilized. That is, hyperconjugation. It is stabilized by hyperconjugation also, right? Hyperconjugation. Last class I explained how hyperconjugation stabilizes the carbocation. Just watch that video, part 2 video, right? You can get it clarity, right? Yeah. Now, so here it is releasing electrons to the carbocation, right? Now it is going to stabilize. But what about here? Here this is NO2 group is bonded. So NO2 group is an electron withdrawing group. Okay. This is a minus I group. There is negative inductive group. Okay. So that's why withdraw electrons. And this electron taken by from this, and it is taking the electrons. Okay, so that's why inductive effect is operated. That is from the source up to third carbons. Okay, yeah. So there is sigma bond electrons are withdrawing the NO2 group. Okay, from here to here. So that's why what happened? The electron is already is crying. Again, the withdrawing group is withdrawing electrons. It is going to be more unstable. So that's why of these two. Okay, which is more stable? This is more stable. This is unstable, right? Okay. Got it, my student? Okay, yeah. So that means you will get a conclusion here. The stability of a carbocation, okay. The stability of carbocation, the stability of carbocation is influenced by electron releasing group and also electron withdrawing group. It is directly proportional to plus I group. Plus I group, electron releasing group is there, increases stability. Inversely proportional to minus I group. If minus I group, if withdrawing group is there, that decreases stability. That means stability of carbocation is directly proportional to plus I group, inversely proportional to minus I group. Is it clear? Okay. That means you can say like this also. That means the stability of carbocation is directly proportional to electron releasing groups, inversely proportional to electron withdrawing groups. Electron releasing groups are responsible for, that is plus I groups, withdrawing groups are minus I groups. Is it clear? Okay. This point you have to keep in our mind, my dear students. This point you have to keep in your mind. So this keep in the box here. Okay. You will get the clarity. This is Kim. Kim means what? Keep in your mind. Fix in your mind. Okay. This is the trick I will give to you. With respect to releasing groups are there, increase stability. Withdrawing groups are there, decreases stability. That is, the releasing groups directly proportional plus I groups. Withdrawing groups inversely proportional minus I groups. Right? Is it clear? Yeah. Okay, now got it? Yeah. Next, we do another concept, that is presence of. This is we did now electron releasing group, withdrawing group. Next, we will go for presence of alpha atom with respect to carbocation containing lone pair of electrons. Right? Can I erase it now? Yeah. Right now, next one. Presence of alpha atom. That is, the stability of carbocation is also influenced by alpha atom. So, for example, with an example, get the concept. Take it here, CH3. Here, oxygen atom is there, and here CH3 is there. And this bond, this oxygen, this carbon, it is carrying positive charge, and to this alkyl groups are bonded. It may be methyl groups, or it may be ethyl groups like this, alkyl groups, or it may be N-propyl, isopropyl, or secondary butyl like this. Okay, these are all alkyl groups are bonded now. Okay, so I'll give you that is which type of alkyl groups, what the influence of that one. Okay. This is already within the second part also, the influence of different alkyl groups, right? Yeah. Now, so now here, so this is unstable, this carbon, 1, 2, 3 bonds only there. This carbon is unstable, it is carrying positive charge. Now here, adjacent carbon is, so carbocation adjacent carbon is alpha. So this is alpha atom is there, alpha atom, it is not carbon, but alpha oxygen atom is there, right? That means, if alpha atom is there, it is having lone pair of electrons, right? Okay. So then this lone pairs of electrons, it is 2 lone pairs are there on oxygen atom. These lone pairs of electrons are delocalized. Okay, okay, they migrate from here to here. They make a bond here. Then you will get your carbon, and here 2 alkyl groups are present. Alkyl groups are present. Then here oxygen atom, it forms a one more bond, and it gets positive charge because one of its lone pair of electron utilized for making a bond here. Then this carbon gets stable now, and here methyl group is present. Now in this, now carbon having how many electrons now? So 1, 2, 3, 4, 5, 6, 7, 8, 4 bonds means 8 electrons are there. Okay, and this oxygen having how many electrons here? 1, 2, 3, 4, 5, 6, 7, 8. In this case, both carbon atom and also oxygen atom, both carbon and oxygen atom having 8 electrons. So that's why it is stable, right? It both follows octet rule, right? Both obeys octet rule. Okay, so that's why oxygen is stable and also carbon is stable, right? That means whenever alpha atom is present with respect to carbocation and it carrying one or greater than one lone pair of electrons, that electrons are delocalized, then that can stabilize the carbocation, right? Is it clear? Okay, so then you can write it, that is alpha atom with respect to carbocation, okay, this alpha atom having one or greater than one lone pair of electrons. It having one lone pair or greater than one lone pair of electrons. That lone pair of electrons are delocalized, they are distributed, they are delocalized, and that can stabilize the carbocation. One or greater than one lone pair of electrons, okay, are present. These lone pairs, these are delocalized and stabilizes carbocation, stabilizes the carbocation, right? Okay, so this group we can call it as plus M group or plus R group. Okay, that is positive resonance effect group or positive mesomeric effect group. Is it clear? That means if a carbocation adjacent alpha atom having lone pair of electrons, then that can delocalize and stabilize the carbocation. That effect we have to call it as mesomeric effect. It is the most dominant. It can easily stabilize as, okay, predominant factor, right? Okay, so this is the influence of alpha atom. This compound is more stable than, for example, they will give like this: the carbon carrying positive charge. Maybe here a methyl group is present. Here methyl group is present, and maybe here there is a CH group is present. Okay, or maybe CH2 CH3 group is present, right? Okay, now they will ask of these two, which is more stable means, so here this is more stable than this one. Why? Because here this is alpha, it is alpha, it is alpha. Here three alpha hydrogens are there, three alpha hydrogens are there, two alpha hydrogens are there. Totally there is 3 plus 3, 6 plus 2, there is 8 alpha hydrogens are present. Then we can apply hyperconjugation effect. Okay, that is I did in the second part. You can watch it when that is. So because of hyperconjugation effect is operated here, and also this is inductive effect. There is methyl groups are there, these ethyl groups are there. There is positive inductive effect is operated here. But if these two are operated, okay, fine, they can stabilize. Okay, fine. But what happens is the predominant factor, my dear students, the predominant factor is, which one is, there is alpha atom having lone pairs of electrons. There is plus M group or plus R group. There is a resonance factor. It is a greater stability than hyperconjugation, which is greater than inductive effect. Got it? Okay, this one you have to keep in our mind, my dear students. Okay, predominant factor. Okay, so this is the trick I am giving to you. You just keep in our mind. Then it is very easy to answer this type of this models of question. Yeah, is it clear? Right? Yeah. Next one. Next factor is percentage of s orbital character. Can I erase it now? Yeah. S orbital character. S orbital. That is, so for example, take it here, the carbon single bond, that is CH3, CH2 plus, okay, and a carbon double bond, here CH plus and here CH2, and a carbon triple bond, here positive charge and here H, okay. So this is these are alkanes. Carbon single bond is there and it is carrying positive charge, and this is carbon double bond is there, that is alkene, okay. So here single bond is there and here double bond is there, okay, and here carbon double bond carrying positive charge, and this is alkyne. So alkyne, there is ion is there, there is a triple bond is present, there is 3 bonds, here 2 bonds, here single bond. So there is a carbon carrying positive charge, that is 3 bonds are present. Yeah. So this is here carbon single bond, right? Okay. So this is what ethyl group, that is methyl group or ethyl group. Okay. So it is a, with respect to this one, this is a reducing group, right? Okay. And here this carbon undergoes sp3 hybridization, and here this carbon have carbon double bond, one pi bond is present, right? This carbon undergoes sp2 hybridization, and here this is 2 pi bonds are present, right? So that's why this carbon undergoes sp hybridization. As it move from sp3 to sp hybridization, the percentage of s orbital character increases. As s orbital character increases, electronegativity of carbon atom also increases. If electronegativity of carbon atom increases, then more electronegative sp. Okay, so here the person, here one s orbital, 3 pairs are participated. There is s orbital is 25%, s orbital character is there, but here one s atomic orbital and 2 atomic pair orbitals, 1 plus 2, that is so totally s orbital character is how much is there? 33.3% is there. Okay, so in case of sp2 hybridization, so s orbital character is how much? 33.3%, and here sp means 1 s 1 p, that is 50%, right? That is 50% of s orbital character is there. So there is 25, 33.3, 50% s orbital character increases. So more s orbital character carbon is more electronegative carbon. If it is more electronegative, then it is behave as a withdrawing nature. Okay, so this is more electronegative carbon. This carbon is more electronegative. Then this behave as a electron withdrawing group. So withdraw, right? Already the carbon is crying. Again, it is withdrawing. It is withdrawing means what happened here? It is withdrawing means then when it withdraw electrons from that, then it is going to more unstable. Yeah, but in this case, this is a sp3 carbon less. It is a electron less electronegative carbon. Electronegativity of this carbon is less. So that what happened? It is a releasing group, right? It behaves as a releasing group. So it releases electron to the carbocation, so that it is going to be stabilized. So that's why these alkanes are more stable than alkenes, which are more stable than alkynes. So this is I gave here. This is a ethane, that is ethyl group I gave now. So this is CH3 CH2 plus. This is a ethyl group. Okay, and this is ethenyl. That is ethenyl. Ene, that is double bond is right. Ethenyl group, and this is a ethynyl group. So that is ethynyl. This is ethyl carbocation, and this is ethynyl. Ethynyl carbocation. And this is ethynyl. Ethynyl carbocation. So ethyl carbocation is more stable, and which is more stable than ethenyl. Ethenyl is greater, more stable than ethynyl. Is it clear? Okay. So this is the concept behind this one. So by applying this concept, we can answer different types of questions from the same model, right? Is it clear? Okay. Yeah. Okay. Yeah. Copy it first. Fine. Next one. Okay. You go for next one. The next concept, distance of the groups. Okay. So the effect of distance of the groups. For example, with an example, you get the concept. Now, what the conclusion will get here? That is the stability of a carbocation. The trick I am giving to you is here. Okay, the stability of a carbocation. Okay, is influencing what? Percentage of S orbital character. If percentage of S orbital character is more, stability is less. That is, stability of carbocation, okay, is inversely proportional to percentage of S orbital character. Okay. So this you have to keep in your mind. This is the trick I am giving to you. Fine. Okay. So stability of carbocation is inversely proportional to percentage of S orbital character. Is it clear? Okay. Yeah. Next one. Distance of the group. Okay. So for example, with an example, get the concept. We'll do now. One, two, three, four carbons. Yeah. So here carbocation, and here, for example, NO2 group is present. Yeah. Distance, right? Okay. Here positive charge is there, and here NO2 group is present. And here positive charge, and here NO2 group is present. Okay. And here positive charge, and here NO2 group is present. Right now. Now, so of these compounds, which is more stable, which is less stable, what is the order of stability? Right. Yeah. The simple thing is here, NO2 group is a electron withdrawing group, okay. Then this is a minus I group, okay. And here, which effect is operated? Inductive effect, because here there is no resonance effect. Why? Because when resonances take place, there is pi bond, sigma bond, positive charge, like that, or sigma. There is a lone pair of electrons, sigma bond and positive, like that. Wherever this is called conjugation. Wherever conjugation is there, then only resonance is taken. But here no resonance. Okay. So that's why the effect we have to operate it is inductive effect. And according to inductive effect is a minus I group. Okay. Yeah. So this is withdrawing nature, right? It is withdrawing electrons from this. So that's why it is going to more unstable. Yeah. And it is also all. That is all in all. Only there is NO2 group is present, okay, in all compounds, in all the given compounds, all the compounds, that is NO2 group is present, it is common. But then how can you decide? That is distance. Inductive effect depends on distance. As from the source, if the distance increases, the effect decreases. Okay, it is become negligible. The effect, inductive effect is negligible. So actually the inductive effect is negligible after third carbon atom. Up to third carbon is operated. After third carbon atom, the effect is negligible. Is it clear? Yeah. So now, so here this is this minus A group. It is present. Okay. It is just adjusted to that one. This is nearer. The distance is very less. The distance is less, so that's why it is more withdraws. Then it is highly going to unstable, withdrawing electrons, withdrawing money from the bank like that. Okay. Yeah. It is a bad friend, right? But here, so this carbon next it is attached to adjacent with respect to carbocation first carbon only. Now this NO2 group is there with respect to carbocation second carbon. Okay, it is bonded to second carbon, so it is withdrawing electrons. So that's why it is withdrawing electrons up to this electron effect is operated. Which electrons are migrated? That is sigma bond electrons. Sigma bond electrons are withdrawn. Okay, so there is migration of sigma bond electrons along the length of the carbon chain towards the more electron into action is called inductive effect. This is the negative inductive effect because the withdrawing nature is there. Right, okay. So by withdrawing the electrons, it gets negative charge. So that's why with respect to the withdrawing group, there is the source atom is getting negative charge. So that's why it is a negative effect. Yeah. So now, so the effect is compared to this one, it is okay, but not that much withdrawing nature. But here, so the distance is from here to here. Okay. Yeah. Then in this case, so it is also withdrawing nature. It is from with respect to carbon 1 to third carbon, it is bonded withdrawing group. The distance is more. Okay, as distance is more. Okay, so it is effect is withdrawing electrons. Yeah, it is happening. This withdrawing electrons. Okay, but the effect is what happened? It is compared to this one. It is negligible. Okay, so this is withdrawing electrons, and is also but the effect is compared to this one is negligible. But what about here? This is with respect to carbocation. The NO2 group is there. It is bonded to here third carbon, and here it is bonded to. It is bonded to fourth carbon. We take it here, fourth carbon. Okay, yeah. So now it is also withdrawing electrons. So sigma electrons are migrated. But keep in our mind, the inductive effect is operated up to third carbon. After that, the effect is negligible. Okay. So that's why as distance increases, here distance is more. But here distance is less. Okay, this distance is less, and here distance is more. As distance increases, the effect is negligible. So that's why the withdrawing nature is not that much can not happen here. So that's why it is more stable. Next one, this second one, next third one, and fourth one is highly unstable. That means what conclusion we get, the trick is here. What conclusion we get is the inductive, that is the stability of carbocation, as the distance from the carbocation increases. Okay, stability increases, right? Distance increases. Distance of the negative group increases. That is, it is directly proportional to distance. Okay, distance of negative group, distance of the electron withdrawing group. Okay, distance. Okay, so it is directly proportional to what? Distance of minus I group. Distance of minus I group. Is it clear? Okay, this have to keep in our mind. This schema keep in your mind. Okay, fine. The stability of carbocation is directly proportional to distance of negative inductive effect group. Fine. Yeah. As distance of the inductive effect group increases, stability of carbocation also increases. Yeah. Distance is less, stability is less. Stability is less because it is withdrawing group. It is more and more withdraws. Distance is less of the negative group. Stability is also less. Is it clear? That is directly proportional. Okay. Got it? Yeah. Copy it first. So, can I erase it now? Okay. Next now, number of the groups now. Now, next, number of the groups. How many number of groups are there? This is distance, now number of groups. For example, the compound is like this. Here positive charge and here chlorine is there. Here positive charge and here chlorine is there. And here positive charge and here 1, 2, 3, 4, right? See, carbon 1, 2, 3, 4, okay? And here chlorine is there. Here chlorine is there, right? Okay. Then one more example. We take it here CH2, here CH3 plus. Here two carbons, there is CH2 plus. Here CH2Cl. Next here CH2 plus carbocation. Here CHCl2. And here this is CH2 plus. And here CH Cl2 and then CCl3, right? Yeah. Now in this case, what you have to apply here? See, first we'll do this one. The carbon carrying positive charge, and here methyl group is bonded. You know, methyl group is the electron releasing group. It is a plus side group. It releases electrons to the bend to the carbocation. So because of that, it is going to be readily stabilized. Fine. Yeah. Next one here. So in this case, this is the carbon carrying positive charge, okay, to this carbon, and here one or two hydrogens are there, and chlorine is bonded. You know, chlorine is electron withdrawing group. It is according to there is negative and negative group, okay. So here conjugation is not there, means there is no conjugation, means there is no resonance effect, okay. So then only here which effect is operated here, negative effect, and maybe there is half hydrogens are there, hyperconjugation effect, but chlorine is there, is a negative effect is operated, okay, yeah. So that's what happened, because of presence of negative and negative group withdraw electrons, so that's why then the stability decreases. Then what happened here, this carbon carrying positive charge, and here how many chlorines are there? 2 chlorines are there. So 2 chlorines are 2 bad friends are there, the effect is more, okay. So this negative and negative, there is electron withdrawing group, okay. So this is negative and negative means what? Electron withdrawing group, withdraw electrons, so the effect is more. So more number of withdrawing groups are there, then it is going to more unstable. Then in this case here carbon carrying positive charge, and here 3 chlorines are bonded, okay, all are withdrawing groups only, they withdraw sigma bond electrons from here, so that's why it is going to more unstable. So that's why as number of negative groups, withdrawing groups increases, the stability of carbocation decreases, inversely proportional, right? Is it clear? Okay, yeah, this is the way how to study the concept, understand the concept. Then it is very easy to do this type of questions appear in the exam, right? Yeah. Now what conclusion we get, ma'am? The stability of carbocation is inversely proportional to number of minus I groups. Number of minus I groups. That is electron withdrawing groups. Number of electron withdrawing groups. Is it clear? Yeah. Okay. That means as number of withdrawing groups are more in number, then stability of carbocation is less. Okay, decreases. So here more in number, here less in number, and between this releasing group it is more stable. Next one group it is more stable. Then 2 chlorines are there. Then 3 chlorines are highly unstable. Right? This is the order. So you have to apply this one, this concept to this. Now it is very easy to answer. You do it now. So here carbon carrying positive charge, and first carbon here only that is there, and the distance, okay, and the distance is same here, okay. So also distance is same. So from here it is attached to first carbon, this distance is same, okay. As distance on all the groups, if distance is the same, then the next factor is you have to see, that is what the next one is, there is the number of groups, okay, number of chlorines, okay. And here this also first carbon is also first carbon, but it is second carbon. So of these two, first carbon, number of groups increases. Here one chlorine is there withdrawing electrons, here 2 chlorines are the withdrawing electrons, okay. So that's why it is more unstable, it is okay, it is somewhat stable than this one. Then what about this? Here distance increases. As distance is the factor here now. So here one chlorine is there. It is also withdrawing, but here distance is less. If distance is less, here distance is less, and here distance is more compared to that one, because it is bonded to second carbon, right? with respect to carbocation, distance is more, here distance is less. Okay, so distance is less means more effect is there. More effect is readily withdraw electrons. Readily withdraw electrons. So that's why. So you can give numbers A, B, C. What the order of stability means? So of this, it is more stable. Then C is more stable. Next, number of groups increases. So that is A is 1. That is next. C is B is highly unstable. So this is the order of stability of these carbocations. Is it clear? Yeah. This is the way how to do it. Next one. Next one is power of the groups now. Power of the groups. Can I erase it now? Yeah. Power of the groups. Right. For example, with an example, we'll get the concept. I'll explain a clear concept. The compound is like this. Here positive charge, and here another group is bonded. Okay. Yeah. You can make it like this also. So 1, 2, 3, 4. Okay. And this is the compound is like this, and here cyanide group is bonded. And here the compound is like this, and here this is another group. It is cyanide group, and here there is a fluoride is bonded. Right. So here there is no conjugation, so that's why there is no resonance effect. And this another group is there, electron effect is operated here. Okay, so it is a minus sign electron group, it is also minus sign group, it is also minus sign group, but the power of the group is different. So among the all, there is another group is more withdrawing power now. Withdrawing nature is more of these three. Okay, and it is okay, and it is a weak. Okay, it is a stronger. It is a strong electron withdrawing power. And capability is there, ability is there, and it is also electron withdrawing group only, but the weaker effect compared to this cyanide and another group, right? So that's why it is a weak effect is there. It is a weaker withdrawing nature is there. So that's why this is stronger. It is a weak electron withdrawing nature is there. So that's why what we will get, it is withdrawing nature is less. This withdrawing is more electrons. There is withdraws. So that's why what happened, sigma electrons are withdrawing. So that's why it is going to more unstable. But this okay compared to this one is stable. So that's why the order of stability is this more stable Cl bonded and Cl cyanide group and NO2 group, right? So that's why what conclusion we get, as the stability of carbocation is power of the group is more and stability is more. Okay, stability is more decreases, right? So there is the power of the group is more, stability less. So that's why the stability of carbocation is inversely proportional to power of minus I group. Power of minus I group. Is it clear? Yeah. Okay. So from all these concepts, different models of questions and concept, I explain clarity. Okay. I think you enjoyed my video. Okay, ma? So then please subscribe it and share to your friends. Okay, then thanks for watching my video, my dear students. Fine.